Okay, welcome back. Back from dinner. We're gonna do, of course, this is Physics 1112. And this is the third lecture for Chapter 9. So let's do this. Chapter 9, Lecture number 3. And we finished up last time talking about uniform electromagnetic fields. We're going to do, in general, not just uniform, but in general. So, in general, an electric field is equal to, and we did this before, we said that it's minus delta V over our distance. I'm going to call our distance delta x. So, and we did it before, and we don't really need to do it again, but minus delta V is just VAB. So hopefully you'll remember that. We don't have to redo that. And so we have that our electric field, well, I think that's not right. We want it over the x, our vector. So that implies this statement. So that is what we can do in general. And now we can find electrical potential voltage in all kinds of situations. We can apply this to just about everything. So let's say we want to look at an electrical potential due to a point charge. So here's our point charge. And we could say that the point charge is Q. And we've got this point charge and some place away from Q at a distance r. We have E, of course, equals K Q over R squared, and V, or voltage, equals K Q over R. Okay, so I'm just stating that, but I think what we need to do is talk about it a little bit more. How did I get this? So let's start with a force. So the force on any charge that we were to put in this position relative to this Q, our force is the distance away, or R, times our electric field. And so that, I'm sorry. It's the charge times the electric field, of course. Which then is KQ over R squared. Okay. When we go to get, so our voltage is equal to R at that point times E, because R is our distance away. D E equals R E, because D equals R, and that equals our V. A, B. So when we do R times E, we get K Q. Oh, I don't want a Q in there. K times big Q over R squared times R. Oh, my hash is out of here. Of course, then that is equal to K Q over R. So we set it here, we used that here, and got this as our VAB and plugged it in there. So at this point, wherever we want to put our test charge Q, we can, and the voltage at that point due to some Q here, it's a big Q. Okay, the heart of that Q, that's our charge. So that's it. It's that easy. We're done. All physics is over. Nope, not quite. So let's leave that. Let's leave that bit. Okay, so let's say, for example, we have a Q that equals minus 3.00 nanocoulombs. And we have an R 5 centimeters. And we want to know what the voltage is. So here's our Q. I'm going to, right in the heart of the Q, that's our charge, point charge. Here's our distance R. And right here is where we want to know V. Okay? So it's cake. V equals K. I don't know if you guys remember. K is 8.99 times 10 to the 9. I can't remember the units. Doesn't matter. We're going to end up with volts. So there's our K. We're going to multiply that K times minus 3.00 times 10 to the minus 9 coulombs. And let's get rid of coulombs, because I don't know the units of that other guy. And we're going to divide out by our 5 centimeters, which is 0.05. Is that right? 155, right. So that's our 0.5 meters. And we do all of that, and it'll end up giving us volts. So what do we get when we do that? Do I need to get my calculator out? No. Well, first of all, this and this are gone. So all we have to do is multiply the minus 0.3 times the 9 and divide by the 0.05. We get a negative 539 volts. So our voltage is minus 539 volts. All right. That's all we need every single time. It's that easy. Okay, it seems obvious to me why it's negative, but why is it negative? Our answer. In other words, why do we see this negative sign here? Okay. Okay, good. So let's think about this. So we have a negative charge, first of all. So you might say, oh, well, it's obvious because this charge here is negative, so it has to be, right? But since it's a negative charge, the E field, let's draw the E field, is pointing toward our charge and away from everything else. And our radius is pointing outward in this direction. And the two things are not aligned. So when you have something that's not aligned, they're anti-parallel. The symbol for anti-parallel is this. So yes, the fact that this is a negative charge, Q is a negative charge, means that it's anti-parallel. So that implies that our E field is pointing away from our radius. And therefore, we have the negative answer. R can never be less than 0. It can equal 0, I suppose, but it always has to be greater than 0. Could be equal, I guess, but let's just say it's always got to be greater than 0 for our sense sake. So since it always has to be greater than 0, the only thing that can change then is the direction of the E field. So, and that direction totally relies on whether the Q is positive or our Q is negative. So that's it. Okay. Moving on. We have an example. And I like this example pretty good. We have a Van de Graaff machine. So let's segment this example. And this one's pretty much straight out of the book. I don't even think I altered it, if I remember right. So example 19.7, we've got our Van de Graaff machine. And you have to draw the Van de Graaff machine right. You got to give all the credit to the Van de Graaff machine. So there's our pulley system with the rubber belt. There's a brush that's attached to the outside of this sphere. This is an aluminum sphere at top. This is insulated housing. Something turns the crank on this thing at the bottom, So there's a little motor, turns the crank, and it takes electrons. Here's another brush. It takes electrons from ground. The symbol for ground is this little guy. And then we can measure the voltage with respect to ground with a voltmeter. And so we have a brush right here, like some metal brush that this rubber is touching, and it allows the rubber to pick up electrons. The electrons get picked up and they go all the way up to the top, and then they disperse into the sphere at the top. And what do the electrons want to do? They want to go to the outside of the sphere and spread out as evenly as they can, and they do it super fast. Super fast. Faster than we might expect. So we have this, and it holds all this extra charge. They're calling it aluminum. It doesn't matter what material it is. Some kind of metal of some kind. The radius of this guy, R, is equal to 0.25 meters. We want to know what V near the surface is. No, I'm sorry. I apologize. V near the surface. So at some point very close, if not just the tiniest fraction of an inch or a centimeter or whatever, a millimeter away from the surface, we have V, and that's 100 kilovolts. I put my hand down, and that's what happens. Okay, so we've got this 100 kilovolts, and the question is how much excess charge is on the surface of the sphere. All right. So the equation of choice at this point would be our V equals KQ over R. We know what V is, we know what K is, we know what R is. So we can solve that for Q. A little handy math. We want the R in the numerator, K in the denominator, and V in the numerator. So RV on K. And we can plug all those things together. 0.25. I'm leaving off all the units. We're going to end up with coulombs. So I'm not putting in units. Our voltage is 100,000. So that's 10 to the 5. 10 to the 5. And we're dividing out by 8.99 times 10 to the 9. And that whole thing is going to be coulombs. So our Q equals that. I don't have any advice in this situation. You just plug it in, I guess. And you get 10 to the minus 6 coulombs. 1.39 times 10 to the minus 6. 10 to the minus 6 is micro. So 1.39 microcoulombs. I want you guys to see the different ones, right? There's nano, micro. It's important. So if you know micro, then you know 10 to the minus 6, okay? So that is our answer. So, good. We've taken it all the way up to 19.3. We've completed it. And we're ready to start talking about equipotential lines. So this is 19.4 and equipotential lines. All right, what does that mean? V is our quote-unquote potential. Okay, it's not our potential energy, it's just called potential. It's not an energy. And as a potential, if we have a charge, there's our charge, and it's positive, so we'll draw the E field lines coming in. This might take a while. Just chill out for a minute. Fast forward. I don't know. It's starting to look snowflake-ish. So, there's our equipotential line. I'm sorry. Those are not our equipotential lines. Those are our E field lines. E field. Okay. Let's see if I can draw a circle. Here, exactly a certain radius away, that's a radius r, we have a potential V, okay? And we can say V at R, right? So depending on the R, you'll have a different V because K, Q over R will be different for the different R's, right? V is a function of R. That's what that means. So that's an equipotential line. The potentials are equal all the way around. Well, there's a lot of things that we can talk about here. First, the graphical representation. So let's get into that. So the graphical representation. Okay, do you remember we did the graphical representation for an E field? And the more, the closer you were to the charge, the larger the E field. And you could tell because of the density out here the density is not very much. In here, we've got more. I've got 3 lines where I used to only have 1. So down close to the charge, you have more density of lines. Well, it's the same thing, only you are the one that has to do it. So here's our charge. Here's our first line. Well, wait, the closer you get to it, the closer the lines are. And then the further you get away, I'm trying to do concentric ones. The further you get away, whoa, got out of control there. The further these lines are from each other. So gradually, you get to a point where the field kind of dies off. So that's the graphical representation of equipotential lines. Equipotential. Let's get rid of this last line here. We went too far. You've gone too far, dude. Okay. So we've got our graphical representation. The same thing if you select a certain circle, the closer you are, the more your potential. Okay? All right. So what are the other things to talk about here? Well, we have plenty of stuff. One of the things is, and I don't know if you guys can tell this, but at every single point, I'm going to use red here. Let's say this point right here. Every single point, we have this E field coming in, and we have the cross field, the equipotential line. Oh, geez. How do I go back? Can I do it? Will I just go back a little bit? No. That's too bad. I don't know what happened just there. My sleeve or something caught it. Looking good. Okay. Well, the point is that at that point, the red point, our fields, we're going to just zoom in on the red point. We have our E field coming through. E field coming through. And we're zoomed in, so you can hardly even tell there's curvature to this. And at this point, we have right triangles, or right angles. Okay? So it's all 90 degrees. Everything is 90 degrees. Every single time you have your E fields, they're always 90 degrees to your equipotential field. No matter what the shape, what the situation, these guys are always... It just bothers me that we have that situation here. Every time they cross at a certain point like this, they're always 90 degrees to each other, perpendicular. So V, that didn't work. V, equipotential V, want to say it, equipotential V. Equipotential voltage is always perpendicular to the E field. That's our takeaway from that. Okay, so we found that our field at every single one of these in these circles is constant. So this is, let's say this is R1. Let's see, R1, 2, 3, 4, 5, 6. This is R6. So V of R6 all the way around is a constant. At that point, E is a constant. E equals KQ over R6 squared. So E is a constant. R is a constant. And V must be a constant. As we get further and further away, of course, you know, as we've gone from, let's say, here's R4, right? So R4 to R6, the voltage is going to decline. So that's okay. We don't care about that. What we're talking about now is purely the equipotential, okay? That's it. We don't care about anything other than what is being equipotential. We're not trying to find the differences at the moment. So let's just let's look at it a different way. So we think of equipotential lines as a curve that has equipotential lines are curves that have the same V potential. Which means if you go from point A to point B, delta V, which equals VBA, equals 0. So, great but I really didn't give you anything extra there. But here's where I'll help a little bit with a picture. So you guys ever look at a topographical map? Topographical. I don't know if you guys go hiking 14ers or any of that other stuff, or at all, but they give people topographical maps. You can get them from the USGA. And let's say you have a mountain, and we're looking at the mountain sideways, like this. Okay? So that's the mountain. And who knows, there might be, you know, scraggly stuff coming down here like that. So that's the side view of our mountain. But if we take, here's the peak, we're going to come down here. This is just to help me map it out a little bit. I'm going to take the peak, and here's our first equipotential lines. And it's closer together like this for a while on the right side. And then it gets closer together more on the left side. And it's steeper on the left side. So the lines are closer together on the left side. How's that? That's not too bad. What a great drawing. Those topographical heights, these are all equal potential in G, in gravity, okay? So these would all be the same elevation all the way around. Same elevation. Well, it's nice. We don't pick situations where our charges are going to do this kind of thing, even though there are places in nature where the fields and the equipotential lines look kind of like this. But we're not going to do anything like that. We're going to keep it simple, right? But these are equipotential lines. Of the gravity field. Because, and I can say of the gravity field just because G equals Gm over r squared, right? So G is a function of r, and as you get further and further away from the center of the Earth, your G changes, okay? So every single time you have the same height, you have the same r, and therefore you have the same gravitational field. Okay. Wow. That went pretty smooth. I like it. And of course, I should note, I said the top one was the side view. Of course, this is top down view. Okay. Okay. Great. I can beat a dead horse if you want, and we can talk about the work of gravity and how that's equal to minus delta PE. And we've already done this before many times, but minus, not quite like this, minus mg HB. So let's say we have point B here, and point A here, and we're going to then subtract mgha for this, leading us to minus mg delta H. We get no work if we go from A to A prime. So if we go from A to A prime, then that means mg delta H equals 0. So that's our equipotential. From A to A prime, all on that same equipotential circuit. Golden. Okay, so along that E field line, do I want to do this? E field lines are the lines of force. Yeah, we need to do this. Okay. E field lines. We're going to just do it with blue. E field lines are lines of force. That's where the forces are going to point. And you can think of that if we look at it this way. If you were to drop a ball off the top of this hill, what's the path of the ball going to take? It's going to go down the sharpest points, right? It's going to want to go down the steepest parts. So at the first, it goes down, to the right, and then it kind of veers, and then it starts going. The lines of force are your E field lines, and they're always perpendicular to the potential. So E field lines are our line of force, and we can see that if our work is equal to FD cosine theta, which equals KQ R squared D cosine theta, F and D are parallel to each other. So the cosine theta is equal to, theta is equal to 0. Theta equals 0. Cosine theta equals 1. And our work equals QED. Because there's Q and there's E. And there's 1. Okay. So it's all because of that. And equipotential lines, however, FD cosine of theta, along an equipotential line, let's just draw a simple one, a circle, and we're going to go from this point to this point. Okay, that's our travel from A to B. And if we're on an equipotential line, it forces the force line and our distance d are now 90 degrees to each other. So theta is equal to 90 degrees. So great, but if this is 90 degrees, or if theta is 90 degrees, that is equal to 0. So our work is 0 joules. So that is how we know we can't have anything at an equipotential. We can't have any work done. So we know that F and D have to be perpendicular to each other. Because we moved, D is not 0. D is not equal to 0. F is not equal to 0. So the only thing that can possibly get us 0 in this situation is the fact that our angle between the E field lines and our potential are 90 degrees to each other. So that's the proof of always being perpendicular. Our equipotential lines are always perpendicular to our electric field lines. So E is perpendicular to the equipotential lines. That seems like a good test question right there. Don't you think? All right. Believe it or not, this takes us to grounding. We've got just a little bit left here, and then I'll either have to record another video or we'll talk about it tomorrow in class. But this leads to the concept of ground, of grounding things. So let's say we have this conductive sphere, and it's a sphere. It's perfectly round with a radius of r, and because it's perfectly round, all the charges want to be spread out evenly, right, all over the outside. I tried to keep them negative signs going in one direction, but it didn't happen. So they're all doing their thing on the outside of the sphere. What does that mean? That means that this is an equipotential line. Okay? There's got to be a symbol for equipotential. Am I just not? Anyway, delta V equals 0 all the way around that circle. From A to B, no matter which way you go, delta V is equal to 0. if we connect this thing with a wire, we connect it to the Earth's ground, then our equipotential equals 0 will be also equal to the Earth's potential. So we have grounded that's an N, that's a U, grounded the sphere. We've grounded the sphere. By connecting it. What does that do for the charge on the sphere and for the Earth and all that? Basically, whatever charge the Earth has, we have the same charge as that does now. This whole thing is called grounding. And whatever happens, when we do that, either the Earth has more charge, it has more E's, so the number of E's in the Earth is greater than the excess here, number of E's in our sphere, or not, but either way, some will go either this way or it'll suck some away from the Earth. We don't know. But in the end, this will be voltage of 0 with respect to the Earth. So the sphere will have a voltage of 0 with respect to the Earth. And that's all that matters, typically, because the Earth is big and it doesn't really hold charge, excess charges. It takes the excess charges and moves them, and we don't know. Nobody knows what happens. No. The Earth has a net charge, I'm sure, but our net charge is with respect to the Earth, and that's all that matters. So technically, for us, we'll just say that it is grounded, and anything that's grounded will have a voltage equal to 0. And that is all that you need to know. 0 volts. Okay, so I think we're going to finish that. We're going to leave that now and save the rest for later. So thank you, guys, for paying attention to this. I hope you got something out of that. And we'll do what they do in France this time. We'll just do that. Okay. See you tomorrow morning.